actually, someone else should have now given this lecture with a different set of slides. Stefan Küttenbaum, who was a postdoc in my group for a couple of years, also did his PhD in my group. But then in March, he left for good, also for a good position. So he will become a senior researcher at the University of the German Army in Munich. So they also do civil engineering. So, and the Army has two major universities also in Germany. So he will still work with us, but so I convinced him I could give this lecture and we could even pay you a little bit. But then last week he fell ill and got hospitalized. So it's not life-threatening, but serious enough so that he couldn't make the slides and couldn't make it here. So that's why I'm now here. Bad for you. So because I had to make the set of slides over the weekend, so it's a little bit more lot of text and probably not as entertaining as one of Stefan Küttenbaum would have been. So he gave me some material, so I hope at least I can explain some of the concepts about accuracy, uncertainty, and probability of detection. So let's see, interrupt me anytime. So it's not a formal lecture at university. Even at university, you should interrupt your professor if he or she speaks nonsense or you don't understand what they are doing. So, okay. So we will a little bit talk about measurement accuracy. This is short. We will also talk about measurement uncertainty, which is quite longer, and how to quantify it, because that's actually the thing we should do if we're doing measurements and if we are giving at the end a number to someone. And then also I will talk about the concept of probability of detection. That's one thing, you have heard this a lot because that's what I'm always talking about at the InfraStar seminars. Okay, so I'm keeping this. So about accuracy. I'm sure you all have a concept in mind what accuracy means. Does anyone to share his or her personal definition of accuracy?
How close the information is to the real?
Yeah, that's actually not bad. That's one possible definition. Actually, there are several ones. So accuracy is not perfectly defined. And also there are a lot of other terms which can be mixed up with it. For example, is something precise or accurate or reliable or whatever. So let's start with something you mentioned. So we are providing a value. We are doing a measurement. We have a measurand. And there are official definitions for that. There's not any kind of discussion about this. So a measurement is an experimental process that produces a value that can reasonably be attributed to a quantitative property. So, for example, I'm measuring a potential difference using a voltmeter, and then this equals to the voltage. And the measurand is actually the property that is the object of the measurement. It has a magnitude and some kind of reference that gives meaning to that numerical magnitude. That's, for example, the unit. So length is meter. The meter would be the reference. And the actual meter, of course, has to be defined and referenced somehow. In the past, it was a block of metal sitting in Paris, somewhere in the basement for a long time. Meanwhile, it's a multiple of a certain wavelength from atomic physics is used for that. But you need a reference of some kind. So example would be determining the mass of a sample by putting it on a balance and then reading the indicated value from the scale. But not only that, but you also have to do some preparations and calibrations, for example, cleaning everything to be sure that nothing else is on the balance, calibration, checking by some reference weight whether the scale is correct or how correct it is. And then you have a measurand, which is the value read from the scale. And the reference would be some international standard, like the international prototype kilogram. So if the scale, what I hope, is referenced to SI units. So this is the American definition, so they also deal with other units. Different terms: accuracy, precision, and trueness. Trueness would actually more close to what you said. How close is the value to the real value? Whatever the real value means in the end. So, because sometimes we don't know what the real value is. So precision would be if I'm repeating a measurement. So how close are the results to each other? But if the precision gets better, it not necessarily gets closer to the true value. So that's a different thing. And if we are combining something which is true and precise, would then be accurate. So that's the kind of graphical idea how to use these terms. See, that's always a distribution of measured values. So, and the average or mean of this data. So, of course, we could also paint this in a different way. So, for example, if this is our axis of the measured value, so we are measuring a lot of times, so we get different values. And if we're doing this a lot of times, we get some kind of distribution, which, as all the mathematicians hope, it looks like a Gaussian distribution or normal distribution. But of course, in most real cases, it's something slightly different. So there are all kinds of distributions. And from here, you could also define, okay, there's a mean value, and the precision could be defined, for example, by something like the standard deviation or the variance or whatever you might want to take as a measure, which also means if you can't say my precision is plus minus 1 volt or plus minus half a meter. You will have also to say by precision, I mean the variance, the standard deviation, or some other kind of things. So we have to give a definition. What are you taking as a measure of the precision? So then, of course, we have the trueness from the previous plot also, which would mean the difference from the mean to the reference value. So to the so whatever we have. While the accuracy would be something which is the difference from any kind of measured values we did to the true value. So different kind of definition also appears in the literature. So if someone tells you my measurements are accurate, you have always to ask, okay, what do you mean? So, and then he or she has to explain what kind of definition did he use, what kind of method did he or she use to calculate the precision, and so on and so on. And of course, always what's the reference? Does anyone know the true value? In many cases, nobody knows, at least not exactly. So that's why these things are kind of complicated.
What's the difference between reference and true?
Pardon me?
What's the difference between reference and true in this case?
Yeah, so the reference is the reference you are taking for your measurements. And that doesn't have to be exactly the true value. For example, for the calibration of a balance, you're probably taking some reference weights which are provided by the manufacturer. But do you exactly know that they are in accordance to the original kilogram somewhere stored? Might not be exact. I'm not talking about cheating or something like that. But it's always that there might be a difference. So the reference might still be, hopefully, very small difference from the actual value. So for many properties in our universe of metrology, there's many true values which are not exactly known. There's always some kind of uncertainty due to the inherent uncertainty of math and physics and statistics. Okay. So while this is a kind of bit blurry for determining the uncertainty of measurements, there's a prescribed procedure. So, and there are different definitions which are but all kind of related because these organizations who wrote the respective codes are talking to each other. So we are talking of organizations which work in metrology. They say measurement uncertainty is a parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurement. So that's somehow, if I'm measuring a lot of several times the same thing, with the same experiment, I get some kind of scattering, and the uncertainty is something which describes this kind of scatter. So it does not include the calibration, so different between this kind of mean value and the reference. That's the thing which has to be done separately. So in different words, a non-negative parameter characterizing the dispersion of the quantity values being attributed to a measurement based on the information used. So, and you will find these definitions in the International Vocabulary of Metrology in this link. There was something like gum or gum up here, so probably have to elaborate on this, and we will talk about this a little bit, because there it's kind of a guidance document which gives us the methods how to do this. So GUM meets, it's over here, guide to the expression of uncertainty in measurement. So, and it was issued together by several metrological societies last time in 2008. So the original is from 1995, but it's updated, but only with minor changes, 2008. And the organization which issues this GUM is the BIPM, Bureau International des Poids et Mesures. That's exactly the organization which keeps these original meter, for example, in its basement. So it's the French metrological authority, I would say. Is that correct? Odile is nodding. So, okay. So, nice thing is, for most standards, you have to pay something. This one is for free. You can download the guideline for free at this website. And I would recommend to do this and have a look at it. I will talk about a little bit about the concepts, but it's a 100+ page document, so we can't go into details here. I just want to talk about the general concept. So, introduction. So unfortunately now a lot of text because I want to bring to you the general ideas. So if someone reports the results of a measurement of a physical quantity, and that's what we're doing, for example, what we have seen, a velocity or a velocity change, that's a physical quantity. So it's, from the point of a metrologist at least, it's obligatory that we also give some quantitative, not qualitative, indication of the quality of the result. So that someone who uses this result can have an idea how reliable it is. So that's probably, when you had physics lectures at school, it was all called error or error analysis at that time, which is similar, but not exactly the same, because we are not talking about errors here, because this kind of scattering might just be based on, on the physics, because we have random processes and some random components in the process. So even if we don't make a mistake, we still have this kind of scatter. So if we are doing an error, correct the error. That's a different topic. So what we are here talking about, if we do everything right, there's still scatter, and we have somehow to assess how these values are scattering, and then giving a quantity for this scattering to the users of what we are measuring. So as this kind of term error is outdated, not used here, that this guide is speaking about the uncertainty. So this value we are giving there is quantity, which gives an idea about the size of the uncertainty. So there again, it says about the error and error analysis, which has been a long part there. So, and I probably also already explained this. So we are still always have an uncertainty about the correctness of the stated result. So next back. So another important thing is it's an international code. It's not a French code or a European code. It's an international code. So they, of course, claim that it's imperative that this method should be the same everywhere. So any kind of uncertainties should be evaluated in the same way by proper methods. And whatever method is used should be kind of universal. So it should be applicable to all kinds of measurements. So it should be independent of we are measuring a voltage, a length, a velocity, whatever. And so there's an error here in this slide. So, and this one slide missing. So, and it should, of course, only use data we have access to, not just some data which are coming from somewhere else. And you should also give references and explain this method. And also the quantity we are giving for the uncertainty should, of course, have a physical meaning somehow. So what have we do to determine the uncertainty? The main thing is, and that's quite complicated, in many of the cases we are dealing here with in USES2, we have to have some kind of physical model for our measurements, a mathematical model of our measurements, so that the quantity we would like to measure is dependent by a certain function, which can be highly complex, nonlinear, whatever we need, depending on lots of inputs parameters. Most of our things we want to measure, for example, velocity change, is depending on a lot of things, not just on one other property. So it depends, for example, on the frequencies we are using. It depends on the places where the sensors are, a lot of inputs. All these quantities, of course, again, have errors and uncertainties. So, and again, also the properties which are in this model we are using may depend on many other quantities. So it can get extremely complex in the end if we're doing it complete and completely proper. So there's two general types of these input parameters. For example, quantities where the values are coming directly from the measurement, from the experiment we are doing. For example, amplitudes, the time series of an ultrasonic signal. If we are using a ruler to determine distance between transmitter and receiver. So these are things we are doing ourselves. But there are also quantities we are getting from somewhere else. They might also be uncertain. So that can be, for example, data from handbooks. If we are using, for example, to evaluate ultrasonic echo measurements, and we are calculating transit time of flight, and then we're using a velocity to convert this to a distance. We can take, in some cases, the velocity from a handbook, from a standard, or from the manual of the manufacturer, or whatever. But again, can we trust these data? We don't exactly know. So we have to think about how reliable, how uncertain these data are as well. Sometimes we have to calibrate our measurement, and then, of course, the calibration process also introduces an uncertainty. All these kind of things have to be included. So before you get lost, I will show an example later on. So that was the theory. So actually, I'm now going from capital letters to the smaller letters, because we knew that first was the math and the physics. That's now the actual data we are measuring. So we're getting some kind of estimate of our measurement from all kind of inputs we have measured as well, or taken from a handbook or a standard or whatever. And if we are doing this, so and then combining all the uncertainties of these values to the uncertainty of that value, it's called combined standard uncertainty. I'm dropping now some definitions on you, but we'll explain, giving an example later on. So yeah, need to evaluate the uncertainties of all the inputs and then combining them. So, and then we have a combined standard uncertainty. which can be a standard deviation, but it can also be a variance or some other measure for the scatter. So all of these input estimates and their uncertainties, they are of course defined by some distribution of all the possibility values. That can be, for example, frequency-based. If I'm doing a lot of observations, I'm seeing how many measurements fall into a certain slots in a histogram, for example. Or I have some a priori information. That's, for example, for a reference handbook. For example, it says, so ultrasonic velocity, wave ultrasonic velocity in steel is from 5,850 to 5,950 meters per second, somewhere in there. So that's also distribution. I don't know where my value is, uncertainty. So, and to evaluate these different kinds of distributions, also different methods are required. And in the GUM, they're called type A and type B. We'll also come back to that. So type A evaluation is simple. That's what we're normally doing. So we are taking a lot of measurements and then we are calculating the variance or its square root, the standard deviation.
Remind me, what's the full name of GUM? GUM? What's the full name?
The short name is Guidance on Uncertainty in Measurements.
Okay.
That's the short name. So the real name is a bit longer, but that's the one which is easier to remember. Guidance on the Uncertainty of Measurements. So this is, we're calculating mean values normally as kind of the expected values, and for the uncertainty, you either take the variance or the standard deviation, which are then also so sometimes called the type A variance or type A standard uncertainty. So first question is variance, standard deviation. Why? And why are we using this? So the variance is statistically the more fundamental quality. It's just the sum of the squares of differences between the measured values and the mean value, and then divided by n-1, so number of measurements minus 1. So that's kind of mathematically more important. But the standard deviation as a descriptor for the uncertainty is easier to use because it has the same unit as the variable. You can say in the end, my measurement is 1 meter plus minus 1 centimeter or something like that. So, but that's in the end up to you what to use. Could also use some other measure, but of course you have to write it down, document it, so that others can follow what you have done there. So that's just the basic formulas here. That's mean value, that's the variance. So that's probably, you should know them by heart maybe, but at least you have seen it before, I would say. So, and the standard deviation is simply the square root of the variance, or sometimes called S or sigma. If you use it as the uncertainty, and the GUM code is called U, so also sometimes a bit confusing what kind of letters are used or what kind of symbols are used. So, but both values are kind of a number which characterizes the dispersion of the values around their mean. So, an even better way another thing which could be used, for example, here in this case is the variance of the mean, which is the variance divided again by n, so by the number of measurements, because that's then depending on the number of measurements. So if I have a lot of measurements, the mean is more reliable than compared if I have just a few ones. So just a few pictures to get the idea into your heads. That would be something measuring a temperature where the actual value is somewhere about like 100 degrees. So, and if the physics says I probably, if I do a measurement, have a normal distribution, we have a mean value and a standard deviation around that one here. That would be math. And of course, if I'm doing real measurements, it looks different. So I have some discrete values and they are scattered around a mean value. But if I'm doing a limited number of measurements, the mean value will not be exactly the same as of the distribution. So the distribution will look a little bit skewed. So, and what we are having here is the standard deviation, plus and minus, and also the standard deviation from the mean, which is a narrower thing. So, but that's the easy part in the end, to look at measured values and then determine these properties. So looking to type B, if I'm having these data from handbooks or where exactly don't know the probability distribution. So, and this kind of information might include previous measurement data. For example, I'm getting data from a previous PhD student where I don't exactly know how he or she has done it. Maybe she didn't do any kind of uncertainty evaluation at all. So then there's what is called experience, or general knowledge of the behavior, properties, or relevance in materials and instruments. Sometimes also put engineering judgment, which says nothing in the end, just says I'm the better expert. So my judgment is that one there. So they are for your devices and then manufacturer specifications, calibration already mentioned, but also data from handbooks have uncertainties. So these kind of stuff. I have this to use as well, but for most of them, I don't have many values where I can do a standard deviation analysis, so I have to do something else. And in many cases, I'm doing something very simple. I'm just assuming a rectangular distribution. For example, if the handbook is saying, okay, as I mentioned, velocity is between this and that, I'm just assuming it's somewhere in between. All values have equal probability. So my mean value is just in the center between the boundaries. And then there's a nice simple formula how to get a standard deviation or later uncertainty from there for rectangular distributions, which is just the span divided by the square root of 3. So you get this from statistics handbooks. So again, we have a measure for the uncertainty of these kind of values. Of course, in most cases, it will be the case that the values in the center are more probable than the one at the edge. So you could also assume a triangular distribution or a trapezoidal distribution. So that depends on how much information you have about the uncertainty of these values. But there are textbook formulas available how to deal with these distributions as well. So it's triangular, so it's not divided by the square root of 3, but by the square root of 6 in these cases. So now I have all these values for all my input properties, all my axes. But I have to give, of course, in the end, something combined, this combined standard uncertainty. And that might be quite difficult. If I'm very lucky, so all my input properties are totally uncorrelated. So one changes, the other doesn't change. Most physics, it's not the case. For example, if I'm changing temperature, a lot of other things will change as well. So let's assume first the simple case. Everything is uncorrelated. I'm getting two values from textbooks and combining them and uncorrelated. So the combined uncertainty is then defined as the sum of all the standard uncertainties of the input parameters multiplied by this term here. Yeah. Now, if you remember at the beginning, I showed this formula about the model, and there was this F. So F is the model. Actually, this term describes how much does my output change if I'm changing the input component, one of the input component. So it's kind of a sensitivity coefficient. So if I have a property which influences the output a lot, then of course also this term here is large, so it has a large influence on the uncertainty of the result. If its influence is small, then also here this term is small influence to the output. So that's the idea. So looks very easy. In many cases, it's not easy because how to determine these gradients is sometimes complicated. Because sometimes I don't have an analytical model for my measurement. It can be something else, or I don't know it all. And then you have to do, again, simulations or experiments, just trying to change your input values a little bit and see what's the outcome on F, and then do it kind of either experimentally or numerically. So both is possible, but that's, again, that can be a nightmare, actually. Because, again, you might introduce uncertainties here. But the concept is quite easy. Of course, it gets much more complicated when the quantities are somehow correlated. I'm changing one, so the other is changing as well. So I'm influencing, by changing one input parameter, I'm also influencing the other, one or many of the other input parameters. So that's why the formula for this case looks a little bit more complicated. So there's some similarities. So the uncertainty of the output. I have these changes here, these derivatives, but now you see it's I and j, so different properties here, and also I have here a different term. This is now not the standard deviation, it's the covariance. In the end, I'm now considering all the effects of if one property is changing, how much is the other changing. So I have a large matrix in the end, checking everything, every input parameter against the other parameters. On the diagonal, there are the variances from the first formula, and on outside the diagonal, there are the covariances, or how much is one of the input parameters changing when I'm changing one of the others. So if you have experimental data and lots of variations for all the input parameters, that's manageable, but sometimes it can also be kind of a nightmare if you, again, don't know about the exact correlations between the input parameters. So admitted, sometimes you have to make assumptions, simplifications, and take some shortcuts. But the shortcut can't be, I'm saying, so say it's accurate. That's the only shortcut which is not allowed. Otherwise, you have to make a good guess for uncertainties, but that would be always on the upper edge, on the safe side. So, but that's the basic idea how it works. So, to summarize this kind of procedure, it's also given the same in GAM. So first, I'm deriving a mathematical relationship between my input parameters and the output parameters I want to determine. And the function should include everything. And also all corrections and correction factors and calibrations and everything. Sometimes, as I mentioned, in several steps. So it can be like a tree function here. So then I determine XE, so that's actually doing measurements of the input quantity, of all the input quantities, either by looking it up in a textbook or by doing an experiment, doing some kind of measurements. Then I'm determining the uncertainties of all the inputs, either by this A or B method. And then I'm checking for any kind of covariances in the outputs, depending, so if the input quantities are depending on each other. And then I'm calculating the estimate of the measurement and the associated uncertainty by the formulas I've just shown. So by one of these two. Sometimes there's an extra. So because I've seen sometimes, so mathematically, my uncertainty might not be very big. So if we are going back to that slide here. Okay, my mathematically uncertainty from all these evaluations might be quite small. So I'm trusting my measurements. That's nice. But then there might be customers, so people who need your data who say, but I see all it might be somewhere, and then I'm running into problems. So that's why sometimes, but this has to be documented as well, people are talking about an expanded uncertainty, and that means simply I'm multiplying my uncertainty by 2 or 3 or something else, which is then called the coverage factor. So just kind of something just to be sure I'm giving a bigger number to include a certain percentage of my measurements into this uncertainty. It's mathematically not needed, but for practical use later on, because people want to be on the safe side. Remember the loose balls in this airplane recently? So where part of the top door flew away. So they probably want to be 100% sure in the end and not just relying, okay, maybe 1 ball is enough or 2, the others can be loose. So that's why in many cases, as I've mentioned, there is some kind of coverage factor to obtain something which is then called an expanded uncertainty, whoever came up with this term. So, and then, very important in the end, documentation. Result of the measurement, the combined standard uncertainty or expanded uncertainty, and then all description what you have done to derive this, so that the next person using your result can say, okay, this value has this uncertainty, and now because I'm using this in another measurement, I can take this as an input quantity with an uncertainty and I can go on calculating. So, sounds like a mess. But if you're providing results in the end of your PhD in a publication or other kind of things, think about all the related uncertainties, especially if we are dealing here with very small velocity changes, always moving on the boundary of signal to noise ratio, very low ones. So think about this. Are you really sure that your measurement is correct? Are there any errors which have to be corrected? But then also where are the uncertainties? And then is my interpreted result later on really reliable, significant, other kinds of things? So it's worth it. And sometimes it also helps. And that's why, okay.
I have a question. If you go back to the slide where you have the formula for the computing the variance out of the variances, either this one or this one maybe.
Yeah.
I know this as a delta method in statistics. I think it's the same thing. Though I know it as a linearization.
Yeah.
So meaning that actually, if we want to use it, you have to basically take this factor, the derivatives, compute it, and then go put in the numbers of where you are exactly on the curve.
Yeah.
And then you can actually get a number. Yeah. Is that right?
You're right there. So that's why somewhere here, probably I forgot to put it everywhere, simplify. So, of course, this is valid only for more or less linear models. If this formula at the beginning gets linear or even highly nonlinear by having quadratic terms, multiplications of the different input quantities, it gets more and more complicated. Then you can't do it that way. Yeah. So, but here for the independent measurements, it should work for the connected ones. There's still methods for that. You can do this somehow, but that's, for example, beyond my expertise.
But for this, we don't need to assume that the individual distributions are Gaussian, because I mean, the standard result is Gaussian, a sum of Gaussians is Gaussian, variance add, but this works even for the non-Gaussian.
That works for all kinds of distributions. Also, how you determine these ones here, the standard deviation, the uncertainties of the single input parameters, that of course depends on the distribution, because you can't use standard deviation if it's not a normal distribution, then you have to do something else. So if you have a skewed distribution or what variable or whatever, so then you have to use another measure and then think about how can they be combined. Of course, that we're doing the same.
Well, I would say if the distribution of your use is very wide, then you run into trouble with the linearization, because then
So
you're always looking at a line.
Yes.
Yes. And this is the curve, direction curve. So the wider your PDF, the bigger range you're looking at, and the bigger mistake you make.
Good. Let's see. So I'm working in a non-destructive testing in civil engineering. So far there's more or less nothing standardized. So and in many testing reports, you don't see any numbers for errors or uncertainties. So and I think that's a problem. Or you see just engineering judgment. Oh, my error for depth of rebar in the concrete is 10% or whatever. If you're asking where does it come from, from somewhere else. Yeah. So in certain aspects, the uncertainty evaluation can help, especially as in civil engineering. Meanwhile, at least for in some more important cases, also for the evaluation of the load capacity of a bridge, probabilistic methods are used. So they need to know the uncertainties of all the input parameters also for their calculations. They can't deal with just numbers. So we need some idea about the uncertainty evaluation. So these are now slides which have been given to me by Stefan Güttenbaum. In fact, it's a conference publication from 2 years ago at a civil engineering conference. So background was the localization of tendon ducts. Who knows what a tendon duct is? Nobody. Okay.
I feel nice.
You should, yeah, okay. Yeah. Okay, so concrete is not just concrete. Concrete is a multi-phase material anyway. So there's made of cement and water and aggregates and probably some chemistry also put in there. And that's a very nice material. It's very good against compression, very bad against tension. So just tensional strength is just 10% of the compressional strength. So, and if you have now a bridge, a long bar, and you put a truck on it, it will bend. It means at the bottom side, it will kind of be tensioned and cracks will appear. Cracks in concrete are a normal thing anyway. So to prevent this cracking, or at least to limit it, you have to put something else inside which gives tensional strength, and that's steel. So you also know these standard bars which are on the concrete, that's normal. But for very long, slender elements, such as large bridges, they are doing also something else. They are putting very strong steel strength inside, and then they are tensioning them, put some grout in the holes where the ducts are, and then they're letting loose so the concrete is compressed. They put some pre-compression on the concrete, so if it bends, it's still below the limit of cracking. And so very sophisticated methods exist to calculate the number of tendons and the placement of tendons. They're not horizontal, they're going in some very sophisticated shapes. But then some construction workers are coming and say, okay, let me put this just inside somewhere. So reality is always different from the design plans. And sometimes just a few centimeters of deviation from the design plans can also mean a couple of percent less or more load capacity. And if you don't know exactly what they are, of course, I have to assume a big uncertainty. So if I could reduce this uncertainty, I will probably, if I'm lucky, gain some better information. At least my information is more reliable. So same questions as we have them, we need to know we have some information and we have to know whether they are true or biased, precise, imprecise. comparable, incomparable as another parameter, also relevant or irrelevant. So not all the measurements someone does are necessary. Sometimes they are actually not needed. And it's evaluated in the way I've just tried to explain. So, and if some of these properties have a high uncertainty, I cannot use them properly. Yeah.
This presentation, it's a conference presentation, it's 15 minutes or 20 minutes.
Is the second part, please?
We should consider a break.
Okay, we can, yeah, probably then it would be a good point to make a break now.
Now?
Yeah.
Okay, so sorry, thank you for reminding me.
Okay. So, but 5 minutes comes. So 10 minutes or?
Yes, 10 minutes.
Yeah. Then good.
Fair enough.
Sorry, everyone.
No problem.
Forgot to.
Sure.
What do we do?
So when I stopped speaking, so I was talking about these matters of true and biased values and precise and imprecise values, comparable, incomparable, relevant, and irrelevant. The part I will talk about is the blue part here, true or biased or precise and imprecise. So that's the things we have kind of under control from the point of the measurements. So remember that for evaluating the uncertainty, we need a physical model or a mathematical model where the output property, which would the position of the tendon duct, so depth below the surface, for example, is depending on a lot of input stuff. So the physical model, probably hard for you to read it here from there. So if the target velocity here is depth, so depth of the tendon duct, and that's calculated by velocity of the ultrasonic waves and radar waves using to do the localization, multiplied by the time of flight, after which the echo appears at my receiving antenna, divided by 2. Very simple thing. So looks like just 2 input quantities. But of course, there's more behind it. So this would be my 2 velocities here, my 2 input quantities here. But again, of course, these properties depend on other stuff. For example, if I'm measuring this time of flight, my system, my ultrasonic system or other system always has some kind of offset, some offset time. Even if I'm putting transmitter and receiver directly together, I'm measuring time because the electronics have a delay and the antennas have a delay and whatever. And also there is some other effects which depend on the type of transmitter and receiver and also some other kind of stuff. But of course, measured time offset is also in there. And this would be one of the properties which, if I'm measuring this a couple of times, scatters around some mean value. So the velocity, that depends. It depends on where I get the velocity from. So of course, you could take it from a textbook, which I wouldn't recommend for concrete because there's a big variation always. So it doesn't make too much sense. I would end up with a huge uncertainty. So I need some other way to determine the velocity. There were several ways. And what was done here is just go to a place where I know where the tendon duct is and taking a reference measurement there. So, the tendon ducts have to be opened at some places anyway to check for the condition or some other properties. Maybe take a sample of the steel, check for corrosion and these kind of things. And then I'm going to this place, doing a measurement there, then I have a reference. So, and then this kind of reference measurement, again, of course, is influenced then by the actual depth at this place, which I can then measure by some ruler or whatever device, probably quite accurate in this case, much more accurate than anything else. But again, I'm doing a time measurement here. So again, this time is also influenced by a lot of other stuff. So that's kind of a relatively small tree still spread up by a simple measurement. So now imagine some more complicated measurements can end up with huge trees, and then you have first to decide which are relevant, which are contributing significantly to my uncertainty, and then you have to start to evaluate this. And after finding this model, then you are going to evaluate the uncertainties of all, for example, the measured times by the methods I have just described. So also Stefan Küttenbaum here used the methodology described in the GAM code. So it is just enlarged the formula. So you see I didn't lie. So it's V times T divided by 2 because wave goes down to the things back up. That's why 2 is here. Because if, for example, transmitter and receiver are not coincident, of course, the formula will become more difficult, like in a multi-offset array or a fixed array, other kind of things, adding to the complexity. So I promised that this would be a little bit of practical example. So this is a bridge in Bavaria where we did these kind of measurements to locate the tendon ducts. See, it's across the river, surface, a little bit complicated here. Here are some girders which are sitting on the pillars. And inside these girders are the hidden, some hidden tendon ducts. So the colleagues responsible for the assessment of the bridge, of course, did a couple of calculations to check, is this really relevant? Should we know the position of the tendon ducts? But they came up after they got the position of tendons from the drawings, that the shape is quite correlated and even quite small deviations from the original position could lead to a totally different stress diagrams, in some cases even being that the concrete might be under tension here, which might lead to cracks. So it's important to know the exact place of the tendon ducts. So in this case, ultrasound. So what you're...
Sorry, very simple question. What is a tendon?
Tendon are the steel strands which are tangent to compress the concrete and to give more strength to the structure. So I will show on Friday. I can show you some examples. We have some samples in the lab. I can explain this more in detail.
Thank
you. Actually, if I remember it right, we even have a sample from this bridge because the bridge was broken down later. At least from a very similar one. So these are ultrasonic C images. This is a cross section of the bridge. There are some tendons which go in the bridge deck. Here would be the cars traveling in this direction. Then tendon ducts appear. More important are the tendon ducts down here. You see these red dots? These are reflections from the tendon ducts by measurements here from the bottom side. So we move ultrasonic devices down here, locating echoes, and there are 2 lines of these tendon ducts here. More or less in line, which is good, not always the case. So sometimes they're deviating also a lot. So that's just to show the numbers. What they needed to know is, of course, depth from the surface, but also from the center of the cross section of the girder, also the distance here. So, which then leads to, again, to this kind of model with the output property would be depth of the tendon duct, velocity times time divided by 2, and so on, with all these associated properties. The reference measurement or the influence on the actual determination of the time of flight. The tree, in this case, is a little bit more expanded, but we'll not go into details here. So that's a lot of work. It's much longer than taking the measurements, probably order of magnitude longer. And some example for the measurements in this time here, it's a GPR, not an ultrasonic device. See here some steel bars inside here. So and localization is done by here, finding the time from these hyperbolas, which are the echoes and the GPR antennas goes here. Ultrasonic measurements look not the same, but very similar. So from here, we're using some imaging algorithms really to collapse these hyperbolas into one point, so to make it easier to pick the time of flight between Bob and Bob. But you see there's some dissimilarities because we don't know the right velocity precisely. Also, the offset time slightly varies here. And so there are all kinds of uncertainties we have in here. Also, what does that mean? Where's exactly the top? Is it here, or is it here, or is it here? So you have to give it a lot of thought, a lot of possibilities to mess up. Then looking at the appropriate distributions. In this case, we had luck. It was kind of a normal distribution to do this. Velocity, in this case, one example would be here. If you take this from a textbook, it would be a uniform distribution. We also could do this by a reference measurement. So you have seen similar things here. Uniform distribution for literature values. If I'm doing reference measurements, again, because I'm doing many of them, I have again normal distribution. So then other things to take into account, for example, which haven't been on scale 4 here, the velocity is temperature dependent. So I have to take this into account. For example, if I do the reference measurement at 0 degrees and the actual measurement and 20 degrees, I will have a problem, slightly difference. All this has to be taken into account. So I have to determine the average for the available values. Then there is some kind of way to calibrate or correct the velocity for temperature, again with some uncertainty. So which then ends up, for example, with an uncertainty of the calibrated velocities of maybe 15 meters per second. If take into account that the real value is around 3,000 meters per second, it's not too much. So it's a small uncertainty, but still I have to put it into all the equations and propagate it back to the output property. So this arrow, for example, would need to uncertainty in the end of the time. This is velocity. The velocity is about 9 microseconds. So this is variance, standard deviation. So then other uncertainties, echo signals can look quite complicated. So where do I pick the time? Again, problem. I might cause an offset or uncertainty. Maybe if I want to pick the real onset of the signal, there's always uncertainty, especially if there's noise. Also over time. So if I have thick elements, the pulse shape might change because I have dispersion, concrete is nonlinear, all kinds of stuff can happen. So you can imagine that this took a while all to eliminate and take into account. So, for example, also the frequency of the pulses changes with thickness of the element. So these are different thicknesses of the concrete element, and for short propagation lengths, I still have the higher frequencies in my signal. Later on, it goes down and down. So that also affects my uncertainty and goes into my consideration. So a lot of stuff. I'm not going into the details here. I'm taking all this stuff, and as I've mentioned before, I have to combine them. And this is the mathematical model again, and then you see a formula which looks a little bit different from the one I've shown you about the correlated quantities, but in the end it's the same. So this is like the combined variances as in the first formula for uncorrelated quantities, but then a second term where they are the covariances, and if you do a math, it turns out it's actually the same. So I end up with some measure of my depth, an uncertainty measure. So then of course I have to use this somehow. So there was an initial model which was taken from the design drawings, and it said, so the expected value, so the depth of the tents, would be 16.3 centimeters, and the error by engineering judgment or whatever was quite optimistic. So 1 centimeter, which means 6.1% error. So now the real model, NDT supported by ultrasonic measurement, there turned out that the expected value, so the depth of my tent ducts was 14.9 centimeters, so a little bit less than what was originally expected, with a slightly lower uncertainty. So just 0.6, which means 4%. So the actual value for the uncertainty by our measurements went down, but also we got a value which is more reliable and more close to the actual value, because the first was just design drawing. So it's probably this one is very optimistic here, this guess. Most cases is much more. So and then what's then done in these reliability models for evaluating the load capacity is to calculate the so-called reliability factors of a certain element for a certain load, whether it would still cope with the load. So, and this is the variance of these values, so the uncertainty of these assumptions. So the original idea would be kind of here, because we had the 16.3 centimeter depth with an error of about 6%. So we would end up with a reliability factor a little bit above 5. Now with our NDT information, 14.9 centimeter, that's why the curve is generally below the other one. So it's less reliable. The bridge is less reliable, not our measurements, the bridge is less reliable. So, but as we were able to reduce the uncertainty, it turned out that we are still on the same reliability level. So we have been lucky. So that's a little bit the problem for selling these kind of stuff to the bridge engineers, because sometimes they don't want to know. Because sometimes you find things which are not in the design drawings, any kind of flaws or missing steel or any kind of things which went wrong with construction. And then the load capacity, the bridge, is of course lower. Sometimes they prefer not to know, because then the authorities have to do something and spend a lot of money. Of course, it can also happen the other way. And then that happened in one case that they assumed, okay, the bridge is defunct. It has to be replaced, demolished first, and a new one has to be built. And after NDT, we could say, okay, there's much more reinforcement than in the original drawing. You can keep it. So, and actually, they kept it. So you can also save a lot of money. Where in the end, the balance will be, or no, the only thing we can promise that in the end, we have more reliable information. Whether the reliability of the structure will be better or not, that's depending on the structure itself. That's not our fault, but of course, we are blamed sometimes. Okay.
We've seen similar things in power station assessments.
Mm-hmm.
The codes and the power station assessments were built on, designed on the smallest detectable defects. So when the NDT gets better and you can detect smaller defects,
Mm-hmm.
they count that as a detection, and then they have to throw things away purely because of the licensing terms. It's horrible.
Okay.
So they don't want to know. They don't want to get better.
Yeah. Yeah. That's okay. So, result of this entire exercise is we have an increased level of approximation to the true value. So I have, based on that, we also get an improved lifetime prediction, because concrete cover is one of the most important values also for lifetime, because the closer to the surface, the higher the risk of water or de-icing salts or whatever getting to these metal elements and then causing corrosion. And of course, we can plan measures, well, not measurements, but measures for improvement or maintenance or whatever. If we see how the structure actually looks like, So, and hopefully we can this way optimize also resource consumption. Okay. How long do I have time until 1:45? 20 minutes or something like that? Or 25?
So, 3:45.
4:45. Okay, so then we'll see how far we can get with this. So, Anthony just mentioned something very important, the smallest detectable defect. So that's one other thing which is very important for the users. And it's kind of used in the concept of probability of detection. So that's a thing which has been used in aerospace especially, and especially in military aerospace engineering since decades, I would say. Yeah. That's an old concept from the 1970s, I think.
From NASA originally, then
That's from NASA. So space and then military aircrafts and then other kind of stuff, which means this description. So to see, okay, what kind of defects can I reliably detect with my technology? What can I promise to my customers? And translate it also that way. So again, there's a nice handbook. So not the GUM code in this case, but there's from the US Department of Defense. So sometimes they do useful stuff. They have issued a handbook which deals with NDE systems and assessment of their reliability. Also free of charge, available at several sources. I just put one of them here. So I also took some information from a German NDT wiki, which is also available in English, and some other sources. So what's behind there? So the behind probability of detection is the idea to characterize the reliability of NDT. Not the uncertainty of the measurements, but the reliability of a certain NDT method for a certain purpose. So, for example, if someone asks the question, is there a crack in my system? So I have to characterize, okay, I can find a crack if it exceeds a certain size, depth, width, whatever parameter is there. So with the desired reliability. Or to measure a specific quantity with the required accuracy. Going back to the previous thing. So is what I talked about previously can also be used to make this POD analysis if I'm talking about quantified properties. So it's calling me. So there is first thing for this hit-miss method, is there a crack or not? Is there a tend duct or not? Is there whatever? So yes, no questions. There are these kind of simple categories. So because my experiment can go wrong in different ways, it can also go right in different ways. So for example, if I have a defect and I'm detecting it, it's called a true positive. If there is no crack, but my system detects a crack and sounds an alarm, it's called a false positive. And on the other way, if there is a crack and it's not detected, it's called a false negative. And if there's no crack, and my system does say there is no, that's a true negative. Sometimes counterintuitive. So I have a defect and I'm talking about something positive. Of course, having a crack is not positive. It's about the detection of the crack. And if I'm detecting the crack, it's of course positive. So that's the way of understanding this. So
about this.
Was the question?
No, it's just the same measure of accuracy and precision.
It's close to it, but here, so I'm so far, and the problem in many cases limit myself to the just yes, no questions, not making quantified measurements of depth or something like that. So for the depth of time. So, and the probability of detection is equal to the probability of the true positives So, which can then be calculated by the number of true positives divided by true positives plus false negatives. So it takes into account here the sum where I'm not detecting a crack. So that's the total number of alarms, so of total number of cracks, and some of them are detected, some not. So, and if it's about a floor size, there's a slightly different formula. Skip some of the stuff to stay at least almost in time. If I'm looking at Gaussian as probability distributions again, because also my systems might vary in a lot of things. So there's also always a distribution that I'm getting no alarm and that I'm getting an alarm. And if I'm getting an alarm and there's a certain crack, these are the true positives. But if I'm getting an alarm and there's nothing, that's the false negatives and so on. That's a way to kind of graphically explain this kind of stuff. The amplitude height in this case might be my system response. Whatever this is, kind of voltage I'm measuring or whatever. So in a perfect expectance situation, it would be the case that the probability of some alarm is 0, and then I have a certain crack size where the system is giving an alarm. So then, of course, it's easy to say here probability detection for above these critical crack size is 1. So my system is perfectly reliable above that kind of limit. Nice. Most cases, it doesn't work, of course, that's why. So in some cases, so if this is the crack size, so for a couple of things, I sometimes will get an alarm, get no alarm, and in some cases we'll get an alarm, but these might be overlapped. So that for a certain range of crack sizes, sometimes I get an alarm, sometimes I don't get an alarm, sometimes I get an alarm, which is of course a problem. I have to deal with that somehow. Causes might be the material is inhomogeneous, there's noise in my measurement system, whatever. All kinds of causes for that one. So that's why in most cases I have no kind of a smooth transition between probability 0, so I won't see anything here for very small cracks. And my system is perfectly reliable for large cracks, so I have kind of a gradual kind of curve in between, which can look like this, but also can look slightly different. But the general shape is in most cases the same. And then for saying, okay, my system for limit of reliability for my probability of detection, in most cases, something is taken like a 90-95, which means in 90% of the cases, I'm getting an alarm, and about 95% of all values are within a certain reliability range. So that's the guys writing these guidelines could have chosen also something else, but that's kind of an agreement and probably enough for most engineering structures. So again, how to determine this probability of detection? That's a lot of work again. More mathematically, for the measurement quantities here, it's a lot of experimental work. Also some theoretical work, but mainly experimental work, because I have to use, for example, a lot of crack sizes, a lot of experimental conditions, a lot of other stuff to really see with what cases do I get an alarm or not, and are these real cracks or not. Important is, it's not to determine the smallest crack the system can find, because I might find some small cracks, but not very reliably. It's more to determine the largest crack the system can miss. And that's a very important concept, because then you said, okay, so any crack which is larger than 10 millimeters is reliably connected. So if you want to make your engineering assessment about your structure, take into account there might be cracks which are below this kind of limit. I cannot reliably see them. So then the engineers can take this into account and design their structures or assess their structures appropriately. So, and to do this, we are establishing a relationship between the probability of detection of the target size or other variables and so on. And then I have to do a lot of experiments to determine the potential for false positives, false negatives, and so on. So not all the experiments have to be real. Sometimes the experiments are also doing by simulations, just to fill the gaps for certain experimental conditions or whatever, because otherwise this analysis is also very expensive. Really expensive in time, but also in euros. So if I'm doing these experiments, either in real or numerical, I have to account for specimen pre-processing, for the inspector, for the inspection materials, the sensor, whatever that might be, the inspection setup, inspection process, imaging consideration, whatever influences my inspection process has to be considered and also varied in all the boundaries which are there to be really sure about the probability of detection. So, which leads to a huge multidimensional matrix of experimental conditions if I'm considering all relevant variables, all appropriate intervals and step sizes. That's why today we're doing something which is called design of experiments. Sometimes we can put experiments together, just don't vary everything separately, but at the same time, especially if things are uncorrelated. So there are ways to reduce this matrix a little bit, but still a lot of work. So skipping some stuff because that's then getting very tedious. For the report in the end, I have to describe, of course, the NDE system which has been used. Because if I'm doing this, for example, for one ultrasonic system, it's not valid for the next one, even if I just change a small thing, like a different probe or whatever, different kind of probe. Then, of course, the experimental design has to be reported, and of course, all the individual and the summary test results. So not done in civil engineering yet, but in aerospace a lot. So one thing which is also important, many people think that the number of inspections of the same object increases the probability of detection, but it doesn't. Very important. So because I have the same uncertainty all the time. So it increases the confidence in my measurements, of course, in my judgment, but not the probability of detection. So if I have a big barrel with red and green apples as a statistical experiment, and then I'm grabbing a few, I get an idea about the relationship between red and green apples, of course, after some time, but I'm not sure what the next one would be. So can be one or the other. So now how to do this then a little bit more in detail. If I've done all the experiments, there are certain conditions in before that, so that these parameters have to be linearized. I will show what that means here, so that the variance of the system responses have a uniform distribution and the observation has to be uncorrelated. So it's a kind of simplification of what we have done here. I will show an example which looks better. For example, lots of experiments. That's the same experiment. So I have one entity system giving me some kind of response, and that's the crack size. So that was originally the answer, crack size, response. I see, okay, you could fill it with a straight line, but it more looks something else. So then simple trial and error things. One logarithmic axis, the other axis logarithmic, both axes logarithmic, and then let's see, okay, what looks most linear? That one, probably. So I'm transforming my variable into the logarithm space to get a linear relationship here between the size of the cracks and my system response. So that helps for the evaluation later on. So, and then I'm ending up with these kind of graphs, which are in the beginning a bit difficult to understand. So these are the values shown in the same graph as before. So one logarithmic axis, the crack size, and the system response. Dots are all my values. And now I'm looking here in some vertical bins about the distribution of values for a certain crack size. And then I'm saying, okay, so let's look here. So a certain number of values have to be above my threshold to be reliable. So for example, here, only a small amount of the distribution is above my confidence level. So probably this will be quite a bad thing. So I'm doing this here. And of course, if I'm going up here, more and more values will be above the threshold level. So I'm translating this, and for each of these distributions, I'm taking the value which is here now above the threshold into a second graph, which gives me probability of distribution, of detection against crack size. So these three graphs here are giving me these 3 points. Of course, I'm doing in reality much more experiments and more denser stuff so that I get a denser coverage of this curve here. So also from here I take so that looking at the statistical variation of these values here, which gives me the standard deviation, but also a 95 confidence bound, so that 95% of the values are between these two lines here. So transforming this to the PhD curve, that not just with many of these evaluations, a lot of crosses, so I get this line, the same shape I've shown before. Also here, these 95% confidence lines are transformed in this graph. And from here, I can easily detect now what I want to have. I want to have 90% probability of detection. That would lead here, the solid line goes up here, 90% would be here. That's a crack size of 10 or maybe 12 millimeters. But to be sure, I want to be sure that 95% of the values are within my range. So I would account for the uncertainty and the scatter of the values. So I'm using the next dashed line here, so which is called then the A90-95 line, going down here, and that's more, it's logarithmic, more like 30 millimeters. So, so for my probability of detection analysis would, sorry, in the end say, so my system is reliable according to this standard for crack sizes more than 30 millimeters. So that's the largest crack I will probably not miss in my investigations. So a lot of statistical calculations in the background. Fortunately, so you don't have to code that alone. So there's, for example, you know, someone knows R programming language, statistical programming language. So an R code is supplied with this code. You can download it and use it for your POD analysis. So there's some starting point available. It even has a very, let's say, simple graphical interface. So latest version, at least I know, is from 2007. So probably a lot of, I don't know whether something in Python or other languages is meanwhile available, but that one is validated and certified. So that's why it's quite often used in practice. Of your NDT system. And these are the so-called receiver operation characteristic curves, which have something here that's the probability of detection, then here on this axis. And this is the potential of false alarms. So, and actually these graphs are used to determine whether your system is actually useful. So if I have something here, so probability of detection is the same as the probability of false alarm. So it's like a random guess, or I can then also roll dice or something like that. So nothing I can use. So a good system would have a curve which looks like this, which has high probabilities, the same with a low probability of false alarms. Also with larger cracks here, I'm ending here that I'm almost yeah, 100%. So, so I'm skipping some other stuff. So to see what's actually done so far. I apologize for the bad quality of the pictures here. Sorry for that. So because we have tried in our group to use this concept to check the performance of certain GPR devices, so radar devices, electromagnetic waves, which are used to detect rebars in the concrete, to see how reliable they are. What's the probability of detection depending on rebar thickness, rebar depth, other parameters, type of instrument for certain devices. So this is a record from a test specimen with rebar at different depths. You see the responses of 5 quite large rebars in this case is at different depths. So normally rebars are within the first 10 centimeters, so 18 centimeters is quite deep for the first layer of rebar. So from a lot of measurements, we determined these kind of curves. This time they look the other way around because the parameter down here is reflector depth. So of course, the deeper, the lower the probability of detection because these radar waves get attenuated and scattered. So that's why it's now the other way around. But from a lot of measurements, you could do similar analysis and could determine that the probability of detection is okay until a depth of about 18 centimeters for this case, which is better than for all these standard rebar locators you can buy in a Home Depot. We also have seen, not surprisingly, that different measurement systems you can actually buy have different performance. So some of them had their limit at 12 centimeters, some 15, some 18. So I have to admit that's 2013. That was the dissertation of Sascha Feistkorn, who now works at the German NET Society. So meanwhile, probably is slightly improved. GPR instruments have gone through some development in the recent year. So one other aspect where this was done in civil engineering was corrosion detection by a method called potential mapping. So where check for the corrosion potential of rebars by moving an electrode on the surface because corrosion is always related to electrical voltage. So, and it's a debated method because sometimes you detect something, sometimes you don't. So Silvia Kessler, now the professor at Hamburg University, did this kind of analysis for many kind of things. So just to show you in the end for several influence parameters. And here it showed up for the size of the corroding area and the probability of detection. For example, these have been all the experiments. You see that it's very slow grading curve. So I have a large area where I might detect something, but not quite reliably. And the real point, the 995 point, might be somewhere here even. So only quite large sizes of corroded patches can be detected reliably. So in sake of time, I will more or less stop here because the rest would be kind of repeating. This was just to demonstrate this analysis can be done for all kinds of methods, all kinds of applications. But the other hint here is, in both cases, these were PhD theses, which means it's a lot of work. So probably we should not expect from you that you do the full uncertainty analysis and the full probability of detection analysis and other kind of stuff, because that would, of course, be too much work for 3 years. But what we would like to you to take into account, okay, I have to think about the uncertainties and accuracies of the stuff we are doing, and I have to give some numbers to it so that the others can work with your results. Okay.
Okay, thank you. The time for discussion or comments? Yeah.
Say the Mill handbook is useful and good, but it also is full of engineering judgments and fudges. So it kind of says, yes, you should look at this and decide if it's linear, and if it's not, you can put something else in, but it doesn't say a methodology to do that, which we're recently looking at. And the assumption of constant standard deviation in the A versus A hat curve leads to some over-optimistic solutions. So there are tools out there, ways that you can have variable standard deviation with size, and then using numerical tools like bootstrapping to propagate through the confidence to understand it. I guess my point is that the Mill Handbook, I think, has given people an overly confident and overconfident prediction, actually, in a lot of situations. They think it's better, the situation is better than it is because of the conservative way it's constructed. But it's super useful as a start.
Do you know a better source?
Oh, no, as a source, it's good. So we're writing a paper at the moment about ways beyond the sort of thing. Okay. Yeah.
For the POD, the threshold is 0.9. So is it a general guideline to set the threshold, or there's a way to?
No, the threshold in the end is part of your measurement system. Okay. So for a different threshold, you might get also different probabilities of detection. But on the other hand, if you're lowering your threshold, for example, to get the smaller cracks, or simplify this analysis, of course, the uncertainty might be bigger because then you have more noise and more also false alarms. So, but it's the threshold is part of your measurement system and part of the analysis.
And second, the POD, I understood it is part of true positive and false negative, I think. So the cases, the measurements, is it kind of biased or insensitive to bias? Because suppose you have 2,000 measurements, I consider balanced data set is 1,000 is with damage, 1,000 is without damage. So for me, this is a balanced data set.
That's actually a good question, because there can be all kinds of biases in this kind of analysis due to the simplifications, and sometimes there's also psychological bias. I think there will be something tomorrow in Maria Bertovic's lecture about this kind of personal bias and the human factor and these kind of things. So, of course, by designing your experiment for this POD stuff, where I'm making a lot of artificial samples with flaws and everything, I can introduce a bias. For example, if I want, of course, want a good result for my system. So in most cases, people put notches in steel or concrete and say that's a crack. So, and this puts a bias because a notch is much easier to detect than a real crack. So you can easily put all kinds of biases in your experiment. And it is actually very difficult to avoid this. So the only thing is, make your experiment as realistic as possible, or even better, let someone else do this kind of analysis. You are inventing a beautiful new instrument, but the guy who does the POD analysis should be someone totally different, not dependent on you. So doing this kind of stuff. So then more biases can be avoided.
Thank you.
Just a comment, and my apologies if I missed that, if you said it already. Another terminology for the POD and the PFA would be sensitivity and specificity.
Yeah.
Specificity is basically 1 minus, I believe, the PFA. And just as an idea, you could also look for those to find literature, because they're also used in other domains of science very much, like in medical stuff, for example.
So I think that's one of the slides I've skipped. So you didn't miss it. I just went over it very quickly. So the specificity helps to see whether your system is sensitive to just a specific type of failure, or whether one of these kind of detections can be also due to other kind of flaws.
Thank So the way I understood the PFA, the POD is that you need to choose a threshold ahead of time. And the way you choose it is by saying, okay, I can tolerate a certain probability of false alarm at the critical defect size. And then you're just plotting the probability of detection. So you're not actually, I mean, this plot does not show what happens to the probability of false alarm. I think what happens is that actually goes down. So this, the value you take is like the worst case, but then actually for higher ones, it goes down. Which is one reason I didn't like it very much, because I come from a radar background and the people do ROC, obviously. But of course, now for the ROC, we see both the POD and the PFA, which I like better. But now it's just for one defect size, right? So I was wondering if what we actually need is a 3D diagram where we show like ROCs as they evolve over the defect size. I don't know if that would be more informative, if that's considered. So, I don't know.
I would agree on that. So both types of analysis have their shortcomings. So combining both would be very clever.
What is ROC that you mentioned?
That was the receiver operation characteristics, stating so whether you have to pay for a high probability of detection, but also high probability of false alarms. And of course, the customers at the end, they want to avoid false alarms because they cost money. So on grounding an airplane, because some engineers say, oh, there might be a crack, and there isn't any, costs a lot of money. Or if I'm doing a repair on a bridge, which is unnecessary, all these kind of things. So having low value for the probability of false alarms is also very important.
Yeah, but I mean, in a sense, having the threshold fixed is almost overly pessimistic, because now for larger defects, you are at a probability of false alarm which is much smaller than you could tolerate. And therefore, I mean, radar, they go for CFAR approach. They'll actually try to make up constant false alarm rates. I guess you can't do that because you don't know what defect size you're looking at. But still, I mean, there's maybe some more to be explored.
There's also relevance specifically for embedded sensing, large area SHM, where the design changes. So a lot of aerospace is driven by POD, a POD requirement and getting the lowest false call rate we can. When you look at very large areas, because you have a large number of sensors making a lot of measurements, false alarm becomes potentially more important than POD, because there's so many measurements happening that you get a lot of them, even if the false alarm rate is very low. So you might actually tolerate a lower POD at the relief of a lower false call. So it's application dependent.
Yeah, that's why aircraft manufacturers are not too happy about having too many sensors in airplanes. So just 2 weeks ago, we had this European workshop on structural monitoring, and one of the conference organizers with me and others was an Airbus manager. They said, so it's like holy water for the devil. So they sometimes don't want to have sensors at some places.
But even the oil and gas people have this concern as well.
Okay, so
thank you.
Thank you very much. So we are taking some time to discuss about the second month. This is for open discussion. Maybe I can show where we are now. We did that during our last meeting. There are some adaptations that are required, and the 1 hour space we have tonight is to discuss eventually with the supervisor, but not many are present. We'll arrange that. And so I can try to share my screen, but okay, so that's just to, because Luigi asked me, can I change my my second month? And you are not the only one, Luigi, to ask. So the second month, when we set the proposal with the supervisors, they are made for you to change of work package, change of country, change from academic to industrial sector. Okay, so it's not comfortable because sometimes it's not really close to your PhD or your topic, but this is meant for training, so that you have expertise in various fields connected to your topic, but not directly your topic. Given that, so you cannot say, well, I'm going with my friend on the same work package because I'm really close to this PhD topic. Okay, so it's possible to make changes. We will discuss this with the project officer, but the thing is not to, it's a challenge to go to another work package, another country, and this is what's thought at the beginning. Given said that, nothing prevents you from saying, oh, I'd like to visit DC07. It's not written in the proposal, but I'd like to visit. Of course, it's open. You can go there for 1 week or 2 weeks to make an experiment, to make some data processing, to visit something, okay? So as far as there is enough money and as far as the supervisor are okay for that, it's really possible. Okay. Then we have issues for some of the doctoral candidates who cannot go to where we thought they would be going because of nationality stuff or what else? This is the main impact, or because they were not there when they were supposed to go in a place. And maybe for Giovanni, Faber, which is an associated partner, is not very responsive. So now that you have arrived in June, maybe they will accelerate to see if you still can go to Faber. And we will see, but I know that Sylvain really wanted Faber to be part of the project and wanted to work on H2 storage. So, okay, so let me share my screen. So I don't know if we have people on the Zoom, Fatima.
You